GPS is a global navigation satellite system that provides geolocation and time information to a GPS receiver anywhere on or near the Earth. For example, your smartphone, where there's an unobstructed line of sight to 4 or more orbiting GPS satellites. GPS is the abbreviation for the Global Positioning System. It is a satellite-based radio navigation system owned by the United States government and operated by the United States Air Force. The GPS is a network of 31 satellites that orbit the Earth at an altitude of 20,000 kilometers, with the purpose of pinpointing one's exact location. The system was originally established for military navigation, although this technology has evolved to serve a function in the everyday lives of millions of people all around the world. Whether it lives in your car or is hiding in your pocket right now, odds are you have used the GPS as a way to find your way back home after chaotically losing your way. But how does a GPS work?
The system that drives the GPS relies on satellites which use atomic clocks, so the information they send out is as accurate as possible.
A GPS device uses signals from satellites in orbit to calculate a given location using the delay and positioning. These systems do not rely on a single satellite. However, 3 or more satellites work together to find an intersection, providing the user's location accurately. Every time you need to navigate from point A to point B, your GPS receives signals from 3 satellites that include the time it took to get there. The time is multiplied by the speed of light, which is how fast these signals travel, and the distance is found. This distance is the radius of a circular area spanning what that satellite is able to see. With 2 satellites, 2 circles are formed which overlap in 2 places. These 2 intersecting points of the circles are the 2 possible locations. A 3rd satellite is added to confirm which of these 2 intersection points is correct. The intersection point of the 3 satellites is then found to determine your exact location. A 4th satellite is often used to correct any errors, improve accuracy, or if the position has a specific altitude. Atomic clocks. This is where it begins to get complicated and where quantum mechanics come into play. It's a given that the GPS requires some mechanism of timekeeping in order to operate precisely, but clocks, whether it be grandfather, wristwatch, or otherwise, have some deal of error. The operation of GPS requires very precise time synchronization to a level of accuracy that requires the satellites to have atomic clocks on board. But what are atomic clocks, and how do they work? First, let's define the second in 3 ways. 1 second can be defined as 1/86,000th of the average solar day, a fraction of the 1900 tropical year, 131,556,925.974/7th. The number of cycles of the cesium-133 atom, 9,192,631,770. That last definition is what we will be focusing on. 1 exact second is the amount of time it takes for a cesium-133 atom in a precisely defined state to oscillate fully, over 9 billion times. Atomic clocks are the result of the perfect oscillation of this atom, and are the most efficient way to keep time, with an accuracy of 1/1000th of a second. So how does this relate to the GPS? Thanks to atomic clocks, the time at which satellites send out their signals are entirely accurate, the absolute correct time. The time must be perfect because 1 microsecond of an error can be translated into 300 meters of a mistake. And we'll see that Einstein's equation of relativity is crucial in this process. This is how atomic clocks work. Cesium atoms resonate at an extremely consistent frequency, over 9 billion cycles per second. There are 2 types of cesium atoms, a high energy level and low energy level atom. In forming the first atomic clock, they heated a stream of cesium atoms into a gaseous state. A magnet is added to separate the high-energy atoms and low-energy atoms. The high-energy atoms are discarded while the low-energy atoms enter a chamber. In this chamber, radiation waves are sent out which change the low-energy atoms into higher-energy atoms. These atoms are once again separated by magnets. However, this time the failed lower-energy atoms are discarded and the new higher-energy atoms are guided towards a detector. Once these atoms hit the detector, an electric current is sent out to electrify the quartz and get it to start vibrating again. The cesium electrons act as feedback to the quartz's oscillations. Every 32,768 oscillations of the quartz equals 1 second. However, this slows down naturally, but that is when the radiation is sent out, changing the lower energy atoms into higher energy atoms, which repeats the process over and over again. The combination of atomic clocks and satellites is the fundamental concept that allows us to have this technology.
To further investigate the implications of quantum mechanics, we can look at Einstein and his theory of relativity. Einstein said that time isn't absolute and that there is no absolute frame of reference, which means no matter what, no two observers will see the same thing. In this case, time for one observer will always be a few ticks different from other observers. This effect is time dilation. It says that time runs different if it experiences different gravitational forces. Scientists use Einstein's theory to calculate relativistic effects that can cause errors in our time. Although satellites don't travel at the speed of light, they do orbit Earth very fast, and the signals they send out are affected by Earth's gravitational force. Scientists take all this into consideration while calculating the time it takes for the signal to reach our GPSs. This way, it is as accurate as possible.
The GPS project was launched by the U.S. Department of Defense in 1973 for use by the United States military. In 1959, the Navy developed the first satellite navigation system called Transit. Its purpose was to locate submarines. In 1963, the Aerospace Corporation used this technology to track fast-moving vehicles on land or traveling in the air. In 1974, the military launched 24 satellites and called the system Navstar. From 1978 to 1985, 11 more satellites were launched, designed to detect the launch or detonation of nuclear devices. At the end of 1985, private companies began to be contacted by the government to develop portable GPS receivers. In 1995, it became fully functional for personal use. As for atomic clocks, the first one was invented in 1948 by the U.S. Bureau of Standards, using ammonia rather than cesium. In 1955, Louis Essen built the first cesium-based atomic clock with the help of the National Physical Laboratory in the UK. How does this technology help society? Global positioning systems have been around in some form or another since the early 70s, and prototypes for this technology trace their origins to several years earlier. Recognizing the need for a more sophisticated form of navigation, the U.S. Department of Defense ran the first GPS with 24 satellites, bringing the project operational by the 90s. Through modernization efforts in the early 2000s, this technology has emerged as the forerunner of day-to-day navigation. Today, global positioning systems are ubiquitous, found in everything from cell phones to car navigation systems. The presence of these devices has revolutionized travel, allowing people on the go to look up local businesses or find quick alternatives to problematic routes they encounter. Stopping and asking for directions has become an anachronism, and while this technology has dozens of military uses still today, it is the mundane simplification of travel that it is most recognized for. Space pollution. Today, there are about 1,071 operational satellites in orbit. This means a whole lot of air traffic and frequent collisions. Remember that this number doesn't account for all the satellites in orbit that are not operational. This man-made space pollution can have a negative impact on the environment, as some satellites have in the past fallen out of orbit, crashing into Earth. This also poses a threat to the International Space Station, as debris, even at the size of a baseball, can cause a great deal of damage if it were to collide with the space station due to its breathtaking speed.
The GPS chip is also very power hungry, which drains battery in 8 to 12 hours. This requires other battery replacement or frequent recharge. The GPS signal does not pierce through the solid walls or structures. It is greatly affected by large buildings or structures.
Due to this, users will not be able to effectively utilize GPS services indoors or underwater, or in dense tree regions or in underground locations.
The GPS is currently being managed by the U.S. Department of Defense, and users are utilizing the system free of cost. It is in the hand of U.S. to allow or deny the GPS service at any time.
Therefore, it is better not to rely completely on a GPS system. Backup travel maps can be useful in the event of an intentional GPS system failure. Sole reliance on a GPS to plot your route can be risky, as it can lead to errors in judgment while blindly trusting the GPS. For instance, a GPS route won't reveal if a stretch of road has great views, is closed for the day, or is potentially hazardous to drive through at certain hours, but stopping and asking for directions at a gas station might give you this information.
Cell phone usage is already at an all-time high, so distracted driving is a huge problem. The GPS just feeds into this problem,
as drivers often find themselves fiddling with the screen. Scientists have already begun developing an even more accurate atomic clock, this time by measuring the oscillations of the ytterbium atom. It is estimated that these clocks will produce results that are 100,000 times more accurate than what is currently embedded in GPS technology.
Self-driving cars and self-flying airplanes are also a huge possibility for the future. If a GPS knows your exact location, it will be easy to make the car drive you and navigate you accurately and safely.
Indoor technology. When you're at home, smart thermostats and lighting systems could use your phone's location to work out where you are in the house, adjusting lighting and temperature accordingly. And finally, out shopping, you'd be able to navigate around a giant supermarket to find things, or the Tesco's app could give you a route based on your shopping list to get in and out as fast as possible.